Hi everyone. So this is the second video for Bode Plot, for sketching the Bode Plot. So in the first video, as you remember, we said that we have different factors in the transfer function. So basically in our h of omega, as you can see here, we have different factors like a constant gain, a pole or zero at the origin, a simple pole and zero, and a quadratic pole or zero. So we said that if we want to construct the Bode plot, we have to plot each of these factors separately and then add them graphically. So in this video, I'm going to talk about how we can sketch each of these factors separately. And then in the next video, I'm going to go through a couple of examples so you can see if we have a transfer function, how we can distinguish the different factors from each other, and then draw them and then add them graphically. And hopefully on Tuesday in class, I'm going to go through more examples so you can be more familiar and more comfortable with sketching the Bode plots. So the first factor that I want to talk about is the constant gain k. Okay, so k, as it is mentioned here, it's a constant. Okay, so it's a constant number. Okay, so for gain k, the magnitude, so the magnitude that we want to use to plot it in the magnitude plot of the Bode plot, the magnitude is 20 log base 10 of k. Okay, so we want to use the magnitudes in decibel, right? So constant gain k, it is already a constant that we can plot it, but we have to make sure that we find the decibel value of that. That's why we will find the 20 log 10 of k. Okay, and what is the phase for the constant? The phase will be equal to 0. Okay, so, and why is that? Why we can say that phase is equal to 0? I know that all of you know that we have a constant, right? So it just has a real part. So this is like k plus 0j, correct? And then if I want to find phi will be tangent inverse of 0 over k, which is equal to 0. Okay? But what if we have negative k? So if we have negative k, the magnitude is still 20 log base 10 of k, but the phase this time will be negative tangent inverse of 0, which is positive or negative 1/8. Okay? So basically, if we want to draw this Bode plot for one constant k, see, I said that before that the Bode plot is the magnitude and the phase of the transfer function versus frequency. So we have the frequency here. Okay, and we will start the frequency axis from 0.1, and then 1, 10, 100, and more. So in the frequency domain, in the frequency axis, we will increase in decades. Okay, so I'll talk about it in a second. Let me first draw the k, the constant k. So we said that the magnitude is 20 log base 10 of k, and the phase is equal to 0. This is 0. Okay, so this is the magnitude plot and this is the phase plot. Okay, so let's see, what do we mean by by decades? So in this Semilog plots, in plotting the Bode plot, you will hear this phrase a lot, per decade. So let's talk about the decade. 1 second. So if I want to write a definition for decade, we can say that it's the interval between two frequencies with a ratio of 10. Okay, what does that mean? So for example, if I want to sketch something in this interval, omega 0 and 10 omega 0, okay, I can say that I am sketching that in a decade. Okay, so you can see that the ratio of these two frequencies is equal to 10, right? The 10 that we have here. All right, so this is a decade. So basically, if we have, for example, 10 hertz and 100 hertz, so this interval in between is 1 decade. Why? Because the ratio of 100 over 10 is equal to 10. Okay? And another phrase that you will hear a lot in the Bode plot is decibel per decade. So basically, I said that in the magnitude plot for the Bode plot, we are drawing the magnitude in terms of decibels, right? So for example, if I say I have 20 decibel per decade, okay, this means that the magnitude changes 20 decibels whenever the frequency changes 1 decade. Changes 1 decade. What does that mean? So for example, if I have this magnitude plot and then this is 0.1, I have 1 and then 10, okay, and here's 0 and then here we have 20 decibels. Okay, so if for example we have this plot, this is just an example, so it's not anything specific. I mean, it is not for a transfer function that we just said. It's just something to show you what decibel per decade means. So if I have this plot here, see, the magnitude, okay, is increasing from 0 to 20 decibels, correct? So basically the magnitude plot, let me just, what I want to do, okay, so here is 0. This 0.1 is for frequency, okay, but the magnitude is starting from 0. So basically this plot here, as you can see, the magnitude of this plot increases from 0 to 20 decibels, right? From 0 to 20 decibels, while the frequency increases from 1 to 10. Okay, so we can say that this plot has the slope of 20 decibels per decade. Okay, so watch these videos carefully before our class on Tuesday, but if you have problems, I can go through all of them again in the class, so it doesn't matter because we didn't have the class on Thursday. I'll go through all of them again for you if you need it. Okay, so just try to understand them, and okay, that's it. So that was for constant gain K. Okay, so now we know what does decade means, we know what decibel per decade means, and we know how to draw the Bode plot, the magnitude and phase plot for constant K. Okay, so what is the second factor that we want to draw? The second factor is pole or zero at the origin. Okay, so let's start doing that. It's a pole or zero at the origin. So first thing that I want to tell you, in the exam and also in your homeworks and in this class, okay, whenever you want to draw the Bode plots, okay, there will be a sheet that I'm going to give you. So when you want to do your homework, you have the book so you can use it, and when you want to do the exam, for sure I will include the table for Bode plots, which is on page 623 of the book. Okay, so if you look at page 6 23, okay, you have table 14.3 that can help you to draw your Bode plots. Okay, so in this class you do not need to memorize all of these. Okay, it's very good to understand them. It is one of the best tools to find out the frequency response of the system. In this class you have this hint, you have this table, so you can use it in the exam and homeworks. But so as I'm saying, I'm just showing you how each of these factors is being drawn like this. So basically, the if you look at that table 14.3, you can see that, okay, for constant k, they said that this is the magnitude and this is the phase. Okay, and the same thing will happen for the simple polar zero and the pole and zero at the origin. So this is kind of a proof to how we are drawing that plots like those that we have in the table. So for this reason, I'm going to talk about factor 2, which is pole or zero at the origin, and also the simple pole or zero, but I'm not going to show you how to draw the quadratic pole because it is a little complex, but you can use that table to draw them. But I don't think that you'll get any of those quadratic poles in this class. Okay, so let's go back. Okay, first thing that I want to talk about here is this origin. So where is this origin? Okay, what do I mean by where is origin in these plots? Okay, where is origin in the semilog plots? So origin is where the magnitude is equal to 0. Okay, so I need 20 log of some omega be equal to 0. This is our origin in the semilog plots, in the frequency plots. Okay, so we know that this is 20 log 10, right? Omega equal to 0. So from here I can say that omega, if omega is equal to 1, then 20 log base 10 of omega is equal to 0. Because we know that log of 1 is equal to 0. Why log of 1 is equal to 0? Because log base 10 of 1, okay, is equal to, so 10 to the power of what is equal to 1? 10 to the power of 0 is equal to 1, right? So 20 log of omega with base 10, if it is equal to 0, it means that omega is equal to 1. So in the semilog plots, okay, in the semilog plots that we have here, omega, this 1 is my origin. Okay, and that's why we are calling this j omega, I mean this factor, pole or 0 at the origin. Okay, so let's draw that j omega. So let's think about a 0. So let's say that we have j omega in our numerator. Okay, so this j omega, you agree that j omega is 0 plus omega j, right? I just added 0, so to show you the complex number that we have. Okay, so if I want to draw this, the Bode plot of this plot, what is the magnitude here? We know that the magnitude is equal to, the magnitude is equal to omega, correct? And then we have to find 20 log of omega base 10 in order to draw our magnitude plot. Why? Because we need the decibel of the magnitude, correct? So let's see. So h is equal to 20 log of omega. So we can put different values for omega, okay, to see what we will get. Okay, so if omega is equal to 0.1, we have h equal to 20 log base 10 of 0.1, which is equal to negative 20. Okay, so when I have omega equal to 0.1, we have negative 20 decibels, correct? And then we go to omega equal to 1, and we already said that this is equal to 0. So this means that this is a 0 at the origin. Oh, I did a mistake here. This is 1. This should be 0. Okay, so this is my 0 here. Okay, and what if I set the value of omega equal, oh, it didn't change the color, omega equal to 10. Okay, so h is equal to 20 log 10, which is equal to 20. Okay, so this means that when omega is equal to 10, the magnitude is 20 decibels. 20 decibels. Okay, so we can draw this plot as this. And if you look at the table 14.3 on page 623, you can see that you have the same thing for this 0 at the origin. Okay, so what is the slope of this plot? The slope, you can easily see that it is 20 decibels per decade. Okay, why? Because so the ratio 1 over 0.1 is equal to 10, correct? So this is 1 decade, and in this 1 decade my magnitude varies from negative 20 to 0, so it is 20 decibels, right? And the same thing happens here. So from 0 to 20, while the frequency goes from 1 to 10, so 20 dB. Okay, so I hope you understand this. And then I'm going to go through the phase to find out the phase. So we have j omega. Okay, so this number is 0 plus j omega. So phi is equal to tangent inverse of omega equal to 0, which is tangent inverse of infinity, which is equal to 90 degrees. Okay, so this is the phase plot for our 0 at the origin. So if I have the frequency and the phase plot, we're going to get 90 degrees for the phase. Okay, and if you look at, let me open the table here. So if you look at that table on page 623, you can see that in general, okay, this 20 decibel per decade will be 20 n decibel per decade. And what is n? N is the power here of this 0. So if we had j omega to the power of 2, then this plot was increasing with the slope of 40 decibels per decade. Okay, you will see in the examples what all of these means, and then it will be easier for you to understand them. So for example, this was the 0, right? So let's look at the pole for 1 second. So what is the pole? Pole is j omega to the power of negative 1, correct? So n is equal to negative 1 here. So our plot should have the slope of negative 20 decibel per decade for the magnitude, correct? So let me just draw the magnitude first. Basically here we have omega, so we have the magnitude plot in omega 0.1, 110. Okay, so we said that This time we have negative 20, slope of negative 20. Okay? So for the slope of negative 20, our plot will be like this. This is 1, by the way. It is 0 at the origin. So this time we have a slope of negative 20 decibels per decade. And you can see in the plots that the phase is also negative 90. Okay, so it is not 90 anymore, it is negative 90 for the pole. Okay, so if it was 0, it is positive 90, and if it is not 0, it is negative 90. So basically, in the table, in the third row, you can see that we have 1 over j omega to the power of n. Okay, and you can see that for the slope, it wrote negative 20n decibels per decade. Why? Because n is equal to 1 when we have a pole, if we write it in this representation, right? If I just bring it up, then it will be like the 0. Correct? That's why it is negative 20 per decibel per decade and minus 90 n. Okay, I hope you understand what I said. So as I said, this was just a proof on how these plots exist on this table, but you will have this table always with you, so you can use them to draw your Bode plots always.